Have you ever wondered how salty seawater, undrinkable due to its high concentration of salt and minerals, can be transformed into ready-to-drink drinking water? What seems like a miracle is actually an impressive technological process, desalination. Let's take a step-by-step look at how a modern desalination plant works, capable of producing millions of liters of clean water every day. A tour that shows how science turns the useless into a vital resource. Every day, a desalination plant is capable of taking millions of liters of water directly from the ocean and converting it into a vital resource, drinking water. This process not only requires advanced technology, but also a considerable amount of energy, as the main objective is to remove the salt and minerals that make seawater unfit for human consumption. In just an hour and a half, this type of facility achieves the seemingly unthinkable, transforming salt water into a clear, safe and healthy liquid for drinking. Desalination is emerging as one of the most practical and effective solutions to the growing shortage of fresh water, affecting many regions of the world. This process involves separating the salts and other minerals present in seawater, leaving it in conditions of purity that meet international drinking water standards. In places where rivers, lakes or aquifers are unable to meet population demand, desalination plants become a key tool. These facilities operate day and night, pumping seawater, treating it, and distributing it as ready-to-drink water. On average, a single plant can produce more than 7 million liters per day, enough to supply thousands of homes and urban centers. Worldwide, there are more than 19,000 desalination plants that together produce more than 45 billion liters of water every day. An impressive figure that demonstrates the magnitude of this industry. The plant at the center of this process is located next to a power plant that uses seawater as a coolant for its condensers. After fulfilling this function, the water is sent through pipelines to the desalination plant, where the real transformation begins. This particular plant, surrounded by the ocean on 3 sides, has an inexhaustible source of salt water at its disposal. The challenge isn't obtaining the resource, but making it drinkable. To achieve this, a sequence of steps is developed that includes collection, pre-treatment, filtration, desalination itself, remineralization, and finally, distribution. The journey begins with the seawater harvesting phase. To achieve this, pipes and pumps are installed several hundred meters from the coast. The choice of location is not random. Points are sought where the water quality is adequate and the environmental impact is minimized as much as possible. The first barriers the water encounters are metal grids and large filters, designed to block floating objects such as branches, plastics, algae, and even marine animals. With a diameter of 63 centimeters, a single pipe can extract more than 15 million liters per day, equivalent to filling a bathtub every second. During the harvesting process, it's not unusual for mollusks, jellyfish, small fish, and crustaceans to be swept by the current toward the water intakes. To prevent these species from ending up in the following stages, additional screens are placed to sieve out any organisms larger than 4 or 5 millimeters. This way, only the water and the finest particles continue their journey to the plant. But even after this initial filtration, the liquid still contains sediment and tiny suspended particles. To remove these, sand filtration comes into play. The water is slowly passed through tanks filled with specially prepared sand. Gravity aids this process. The microscopic gaps between the grains retain the particles, allowing only the water to pass through. Although it now looks much cleaner, this water still contains particles invisible to the human eye. To enhance its purity, a complementary technique is used: the addition of chemicals such as sodium hypochlorite, a disinfectant, and iron chloride, which acts as a coagulant. The coagulant's function is to group solid debris into small masses called flocks, which settle and are more easily removed. The water then passes through an aeration system in which jets of air agitate the sand, improving filtration. In this stage, even microscopic particles equivalent to 1/10 the width of a human hair are removed. Once this phase is completed, the water is temporarily stored in enormous tanks of up to 500,000 liters, ready for the most challenging step: salt extraction. Salt is difficult to separate because the sodium and chlorine molecules dissolve completely in water. To break this bond, the most widely used process in the world is reverse osmosis. This is where technology truly shines. The water is subjected to enormous pressure, approximately 60 bars, equivalent to 60 times the atmospheric pressure at sea level. To achieve this level of force, centrifugal pumps are used, which propel the water through conduits encased in semi-permeable membranes. These membranes act as ultrafine filters. They allow water molecules to pass through, but block salts, minerals, and other dissolved impurities. Inside each reverse osmosis tube are several membranes arranged in a spiral. This configuration is no coincidence. It maximizes the space inside the tube and at the same time increases the surface area in contact with the water, improving filtration efficiency. Each tube can contain up to 8 membranes made with ultra-thin plastic layers that act as a selective barrier. What's most striking is the microscopic scale of its pores. These holes are so tiny that they're 100 times smaller than the width of a human hair. This difference in size is crucial to the process because only water molecules are small enough to pass through them, while salts, minerals, and larger impurities are retained on the membrane's surface. The effect of this technology is surprising. Approximately 99.8% of the salt present in seawater is trapped, meaning that almost all the dissolved sodium and chlorine are removed at this stage. As a result, 2 clearly differentiated streams are formed. On one side, purified water appears with a minimal salt concentration and ready to undergo final purification adjustments. On the other, the so-called brine flow emerges, a flow with even higher salinity than the original water, as it concentrates everything rejected by the membranes. In practical terms, the performance of this system can be summarized simply. For every 2 liters of seawater entering the pipes, approximately 1 liter of seawater exiting the pipes, liter of fresh water and 1 liter of concentrated brine are obtained. This ratio demonstrates both the effectiveness of reverse osmosis and the need for proper treatment of the waste generated. Brine management is a key issue. It cannot simply be released back into the sea uncontrolled, as this could disrupt the ecosystem. At this plant, the brine is carefully diluted and returned to the ocean in coordination with the neighboring power plant, which already uses water for cooling. This avoids abrupt changes in the salinity of the marine environment. Meanwhile, the solids and waste retained in previous phases undergo additional processes. They are allowed to settle in large tanks, pressed to recover the remaining water, and finally transferred to controlled landfills. The water obtained after undergoing reverse osmosis no longer contains salt, making it much safer than its original state. However, it is not yet completely ready for consumption because this procedure, although very effective, also alters certain natural properties that must be corrected before distributing it to homes. One of the most important adjustments is pH balance. During reverse osmosis, water can become too acidic or in some cases too basic. An inadequate pH level not only changes the taste, making it less pleasant, but can also cause corrosion in pipes and affect the distribution network infrastructure. To prevent this, small doses of acids or bases are carefully added until a neutral level is achieved, safe for human consumption. Another key aspect is remineralization. When water passes through osmosis filters, it becomes an extremely pure liquid, so pure that it loses most of the natural minerals normally found in rivers or springs. Although this may seem positive at first glance, it actually creates tasteless water, lacking the fresh taste we're accustomed to and with fewer essential nutrients. For this reason, minerals such as calcium and magnesium are added, which play a key role. These not only improve the taste of the water, giving it a more natural profile, but also help maintain bone health, muscle function, and overall body balance. They also increase alkalinity, making the water more stable and reducing the risk of corrosion in pipes and tanks. With these final adjustments, desalinated water ceases to be a chemically neutral, characterless liquid and becomes a balanced, safe and enjoyable resource, ready for distribution and daily consumption. As a final safety measure, a controlled dose of chlorine is added. Although the water has already undergone prior disinfection, this step ensures that bacteria do not develop during storage or distribution through the pipes. Every time a batch of water is obtained at the plant, it is not immediately sent to the distribution network. Before that, it must go through a strict quality control and verification phase, designed to ensure that the liquid meets all the established requirements to be considered suitable for human consumption. At this stage, the water undergoes a series of analyses that evaluate various physical and chemical parameters. One of the first aspects checked is turbidity, i.e., the degree of water clarity. This indicator reflects the amount of suspended particles and allows for the detection of any remaining tiny solid residues that could affect both the aesthetics and safety of the resource. Another key factor is the concentration of total dissolved solids, TDS. This measures how much salt and minerals remain in the solution after the entire desalination process. The goal is to ensure that the level remains within the limits recommended by international drinking water standards. In turn, specific tests are performed to identify the possible presence of heavy metals such as lead, arsenic, mercury or cadmium. Although these elements can be found in trace amounts in nature, they are toxic if they exceed certain levels, so their control is essential. In addition to these variables, complementary tests are performed to evaluate parameters such as pH, electrical conductivity, residual chlorine concentration, hardness, and the presence of organic compounds. All of this is done under strict protocols that follow the guidelines of national and international regulatory agencies. Monitoring does not depend solely on laboratory technicians. A centralized computer system continuously monitors the chemical composition of the water throughout the entire process. This software receives real-time data from sensors located throughout the plant and allows immediate response to any deviation from normal values. Once it passes all the tests, the water is released into the distribution network, reaching homes, businesses, and industries. This entire process, from the moment the water enters the sea until it becomes potable, takes approximately 90 minutes. Today, nearly 300 million people worldwide depend on water produced by desalination plants. What once seemed like a futuristic solution is now an everyday reality in regions like the Middle East, Spain, Australia, and the west coast of the United States. In just 90 minutes, water travels a path that begins in the ocean and ends at city taps, a process that combines engineering, chemistry, and advanced technology to transform what was once salty and unusable into an essential resource for daily life. Desalination not only solves the water shortage in arid regions, but also represents one of the most important solutions to the global challenge of water scarcity.